All right, I want to figure out how to choose k slots from n total. We're continuing this problem of the basketball player. And with the 2 out of 4 foul shots, what we did was we figured out that we needed to solve a little counting problem. How many ways can we fill in 2 slots with S's and the rest with F's in 4 foul shots? What if we had a bigger number? What if we were choosing 3 slots from 5? Well, the first thing that we did up here was instead of just writing out SFSF, FFSS, we could symbolize that by, okay, let's say the first and the second slot are S, or the first and the fourth slot. Using numbers is it just makes it more easier to figure it out. Okay, so here's another example that should get the basic idea that goes in general. Let's choose 3 slots out of 5. So we just got 5 numbers, 1, 2, 3, 4, 5, and we just want to figure out how many ways can we choose 3 of those numbers. And remember, we don't care about the order that we pick them in. But what we discovered in the last video is that if we actually first count them with order, it might be a good idea. And we got, in this case, there was a kind of a clever way to do it. We're going to do a little bit different way in general. By putting them in this grid, we could see that they're matched up. And we just needed to count them with order, 4 times 3, and divide by 2 to get 6, which is the correct number. Okay, so that's the idea here. And I've spent a fair amount of time writing these tables down by hand. I probably should have had a computer do it. Here's one way we could choose 3 numbers out of 5 with the order mattering. So, for example, if 3, 4, 5 is listed separately from 5, 4, 3, etc. Okay, and I just listed them in alphabetical order. Okay, that's a good way to get the total number, to see the pattern for the total number. Okay, here's the pattern. Notice that everything on the top row starts with a 1. Everything on the second row starts with a 2. Okay, so the rows, how many rows are there going to be? There's going to be 5 rows. Okay, we have 5 choices for the first number. Okay, so that's going to be one way, the start of our counting process. There's 5 choices for the first number. It can be 1, 2, 3, 4, 5. Now, that means we just have to figure out how many are in one row and do it systematically so that the pattern will scale up to the general case of k slots in n total. Okay, now let's look at the first row here. They all start with a 1, so that's boring now. Now, how many choices are there for the second number? It could be 2, 3, 4, or 5. It can't be 1 because, remember, these are supposed to be distinct numbers. We're picking without replacement is the terminology here. But everything else is fair game, so there's 4 possibilities. Okay, now let's just look at one of these sections. This is where he picked the first number to be 1 and the second number to be 2. And we know that there's 4 identical triplets. There's this triplet, this triplet, this triplet, and this triplet. And we've already accounted for that. So we just need to figure out how many choices are there in here. Oh, well, we've picked 1 and 2. How many left? 3, 4, and 5. So there's 3 possible choices. And that pattern continues throughout the whole table. So, for example, in this row, which we've already accounted for being there because of the 5 here, there are still 4 triplets based on what the second number is. 1, 2, 4, or 5 are the possibilities here. And each of those triplets has 3 possibilities for the last number. Okay, so very simple pattern. So in general, we're just going to get picking n things. We're going to have n times n minus 1 times n minus 2, and just continue until we've picked enough things. Okay, so this gets a name. This is called 5 pick 3. Okay, that I'm picking, and pick means with order. And it's just very simple. It's just the product of 3 numbers starting with 5 and counting down. Okay, so that's not what I wanted, though, because remember, this was counting them with order. So the 1, 2, 3 and the 2, 1, 3 are counted separately, and I don't want that to happen. And the 3, 4, 5 and the 5, 4, 3 are counted separately. If I'm really just saying, this is really a code, remember, for how many ways I can write down like SSSFF or SFSFS, 3 S's and 2 F's. It doesn't matter what order I put the labels in. If I say there are S's in slots 3, 4, and 5 out of the 5 slots, that's the same as saying there's S's in the 5, 4, and 3 slots. Okay, so I need to correct for a pretty substantial overcounting here. Here's how we do that. I wrote this down in a different order. It's the same pattern, it's the same numbers, just written in a slightly different pattern. What I did was I took all the things that have just the number that just use the numbers 1, 2, 3, and I put them in a column. And here's all the ones that use 1, 2, 4 in a column. Here's all the ones that use 1, 2, 5. Okay, so really we just want how many are in one row of this diagram. And the funny thing is, it's kind of tricky to calculate that directly. But we can actually do that very nicely based on this result we have already. We know how many things are in the table here total. I never actually calculated that. It's 60 in this case. Okay, there's 60 things in the table because it's just the same table of numbers, just regrouped. Okay, now if I just divide by how many things are in each column, then I will get the correct count, because I really just want to figure out, whoops, I don't want to do that. I just want to figure out how many are in one row, because that's exactly all the ways I can count them, but not duplicating in terms of order. Okay, so I can do that. Okay, it's going to be 60 divided by, okay, now how many things are in one column? Well, it's obviously 6 in this example, but let's do that systematically. Turns out to be the same exact principle that we just used over the top table. Okay, I've got 3 slots now, okay, and exactly 3 objects, and I just want to pick, okay, the 1 can be in the first slot, or the 2, or the 3. Okay, that's 3 choices. Or the 2, well, so now let's say, suppose I've picked the 1 to be in the first slot. Now, there's 2 choices for the second slot, the 2 or the 3. Look familiar? It should. Okay. Now, suppose I've picked the 1 and the 2. How many choices are there for the third slot? Remember, I'm only looking at this column, so the only choices right now are 1, 2, and 3. There's 3 slots and 3 numbers to put in. So once I've picked the first 2, the last one has only 1 choice. Now, it might seem a little silly to put in times 1, because it doesn't do anything in terms of the number, but it shows the pattern. Okay. So we're correcting the overcounting by just saying, okay, now that I've got 3 objects, how many ways can I just reorder? It's called permuting. That's the technical term. How many ways can I permute those 3 objects? It's the same exact principle of count the number of ways for the first one, then the second one, which is 1 less, then the third one, which is 1 less. Okay. And finally, we get the right answer. 60 over 6 equals 10. Okay. That's how many ways you can choose. So remember the terminology there. It was 5 choose 3, and that's equal to 5C3 in one notation, or there's this other notation where you put it in parentheses, and that's the notation that's more common in sort of advanced math books, but it's not what the calculator uses. Okay, and so that's equal to 10. Okay, so in general, here's the idea, and we're going to need that for our next problem. In general, n choose k is going to be, you take a fraction, n times n minus 1 times n minus 2 down to, well, this is a little tricky. I've got to put, the simple way to remember it is I just put k numbers up here, because I'm picking k things. This was with order. And it's a little tricky. It turns out to be n minus k plus 1. Okay? But you can just remember it as I'm writing down k things here. So notice if k was 2, I'd go n times n minus 1. And that's not, the 1 is not equal to k. It's 1. You subtract and then you go back up by 1 by adding 1. And then dividing by, what we were dividing by? Okay. We were dividing by just starting with k, the number of things we were choosing, times k minus 1 all the way down to 1. Okay, so that's k times k minus 1 times k minus 2, ... Okay, well, and then down to 3 times 2 times 1. Now, it turns out there is a nice abbreviation for that, for the bottom there. Okay, let's leave the top alone. This is called k factorial. Okay, and let me just make a note up here. There are k factors on top, just to remind you of that. Okay, so this is a perfectly good formula for n choose k. Turns out, with a little bit of cleverness, it turns out you write it all in terms of factorials. You can pretend that you're going to write all the numbers multiplied n all the way down to 1. You still need to divide by k factorial, and it turns out if you also divide by n minus k factorial, then it cancels out the ones you don't really want on the top. I'm not a huge fan of this formula in this mathematical context, because I think this one is actually sort of more instructive. But this one takes fewer symbols to write down. Okay, and this is the master formula you'll always see. Luckily, the calculator will calculate this directly. It's in math prob, the probability functions. Okay, so that's a little demonstration of why this bizarre formula pops up in the book at this point. Why, when you've got to figure out how many ways you can choose certain things out of a certain number of things. Okay, so let's use that real quick before we wrap up this section of the video. Okay, making exactly 7 out of 10 foul shots. Okay, so the probability of 7 out of 10. Remember, that's the probability of like success, 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 4, 5, 6, 7, plus the probability of, in some other order, 1, 2, 3, 4, 5, 6, 7, and then another fail, something like that, plus dot, dot, dot. Okay, it's the sum of all those probabilities. Okay, but how many ways are there to fill 7 slots out of the 10? That's got a name now. Okay, and I'm going to use their terminology for it. 10 choose 7. Okay, and then what's the probability of 7 successes and 5 failures? We've got the 7 successes and the 3 failures. Yeah, 7 plus 3 is 10, not 5. Okay, and then we just have to figure out what that is. Okay, well, 10 choose 7. It's 10 times 9 times 8 times 6 times 5 times 4 times 3, right? I've got 7 numbers up there, over 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so this would be if you made the analog of that first big table in alphabetical order of 7 numbers picked from 1 through 10. And then we correct for the overcounting by dividing by how many ways could we reorder each column, like in the second table that we had before. Okay, notice there's a lot of cancellations there. We'll do those in a second. 0.70 to the 7 times 0.30 to the third. Okay. Now again, this calculation you do not have to do by hand if you've got a calculator, but I wanted to do at least one by hand to show you they're not as intimidating as they look. Okay, let me just copy it and then show you what happens. Notice there's a lot of cancellations here. The 6, 5, 4, 3 all go away. Okay, and for some reason I've got a 7. I missed the 7. I thought that was weird that it was ending with 3. It was totally wrong. That's why. Okay, 10, 9, 8, 7, 6, 5, 4. There's 7 numbers. It's still correct that there's 7 numbers up there. I just skipped 7 for no good reason. Okay, so the 10, 9, 8 stay, and then the 7, 6, 5, 4 go away. Okay, so it's actually not too bad. It's 3 numbers over 3 numbers when you simplify it. Okay, and so that's going to be 720 over 6 is 120, as it turns out. Okay, and then certainly I want a calculator for this part. So about 27% of the time. So notice that this is not a guarantee. Even though he's a 70% foul shooter, it's definitely not a certainty that he will make exactly sort of the expected number of foul shots, 7 out of 10. It's actually only a little over a quarter of the possibilities, because he could make 8 or 6. Those are pretty likely, and of course he could make a small or a big number as well. But here's the number. Okay, so the key is this kind of formula, and I just wanted to make sure that I explained a little more than the book does about where the heck this mysterious thing, and especially this mysterious formula, comes from. It's really a shorthand for this, and we've seen an example where that comes from. Okay, I'll finish the rest in the next video.